Welcome to Recitation, Chapter 4. This chapter is going to focus on stoichiometry. And so we will be discussing how much, and we'll learn how to calculate how much from chemical reactions. You'll see that A and C and E are type of chemical reactions. So you're going to have to learn how to write some chemical reactions and recognize certain kinds of reactions and balance these chemical equations. And from these chemical equations, when we're given grams or moles of one substance, we can calculate grams and moles of another substance through these types of reactions. And a lot of these problems will all have a thing called limiting reagents, limiting reactant, and excuse me, how we'll recognize those is we'll see that there's two amounts, whether they're grams or moles of both reactants. And in each case, we always will do the same thing. We'll convert each one of those substances to the moles of product. And then whichever one is the least amount of the moles of product, that is the one we'll work on, or towards when we're answering the problem. So I will go into that in more detail. So just to tell you, you're going to need to memorize your table 4.1 on page 161. These are your solubility rules. You're going to need that to answer probably, I don't know, 3 or 4 questions on the exam would be my guess. So make sure you know your solubility rules. And the other formulas that you're going to have to be able to apply, and we don't have any dilution problems here, but I'll just go ahead and tell you, if you work dilution problems, M1 V1 equals M2 V2, that is a formula that you just kind of memorize. And we're going to talk about molarity, which is big M. And every time you see molarity, which I'll write out molarity, you need to go ahead and make that a conversion factor. Moles of whatever it is over liter of solution. And if you get used to doing that and making that as a conversion factor, that'll make these problems easier to solve. And finally, I want one more thing you'll need to memorize for formulas in this chapter is percent yield. Percent yield, and that is A over T times 100%. And A is actual yield, and then the theoretical is on the bottom for T, theoretical yield. So you'll have to know that formula. The problems that are due for this recitation will be problems 4-1, 4-9, 4-11, and 4-14. And these will be your participation points. Upload those into Canvas as a PDF file. Okay, let's start going. Okay, the first reaction has to do with oxidation reduction. Redox. So this is section 4.9, and that's page 175. And this problem will be due. It's a 4-1 problem. This is important to know how to do, so for the exam. Now, what I always do when I see oxidation reduction, I have a mnemonic, Leo, Ger. Maybe some of you have heard that before. And Leo stands for loss of electrons, is oxidation. And Ger, it's like think of a Leo the lion going grrr. The GRE is for gain of electron, and that's reduction. So you can't have oxidation without reduction. So one of these elements is getting oxidized, and one of them is getting reduced. They do it to each other. One of them is taking away the electron, and one of them is gaining the electron, because oxidation reduction is really where is the electron going. And you have to be able to take a reaction and identify where what element is being oxidized and which is being reduced. And that's what it's asking here. And in order to do that, you need to memorize your rules on page 177. And so those rules are about oxidation states. So the way you solve this is you're going to assign oxidation states. So going over those rules real quick. Number 1, if you have a free element, its oxidation state is 0. Number 2, if it's a monoatomic ion, it's whatever its charge is. Do you remember you had to memorize the polyatomic ions? Well, this monoatomic is whatever its charge is. So like sodium plus would be a monatomic ion. When you're given charges, see, the free element is by itself. But when you're assigning charges, this is going to be when you see them in a compound. That's the only time you're going to see them with a charge. Because you're not going to get just silver plus or sodium plus by itself in nature. It's going to be attracted to an anion, like chloride, bromide. Okay, number 3 for our rules. If you have a compound, the sum of the overall oxidation states must either equal 0 if it's a neutral molecule or whatever the compound is. So if it's an ion, like a polyatomic ion, it'd have to equal the charge. And then number 4 of the rules, metals are always going to be a positive oxidation state, oxidation number. And if they're group 1A, it's going to be +1. If they're group 2A, it's going to be +2. You had to memorize a lot of this already when you were writing ionic compounds. Number 5 for your rules is it's a table. The non-metal table, it's actually not even numbered, but the table is on page 177. And whenever you see fluorine, it's a -1, fluoride. Hydrogen is +1. Oxygen is 2-. And then if you have 5A, group 5A in the periodic table, it's a 3-. So it'd be like nitrogen. 6A, like oxygen, would be 2-. And 7A is all your halogens, which are 1-. So the first thing you do is you recognize it is an oxidation reduction problem. How I recognize this is I see an element by itself with a compound. So I see a free element and then it's in a compound. And that's typically how you recognize them. Because how are you going to recognize it in front of precipitation reactions? And then you have titration, neutralization reactions. So the way I see it is I find, oh, look, we have a free element. And we have a free element on both sides of the reaction arrow. And I think, oh, this is an oxidation reduction. And so to start signing oxidation numbers, I always find my free elements first. So as you can see, zinc is going to be 0 because you can look on the periodic table and you see zinc by itself. And then silver is going to be 0. Then silver over here on the reactant side is going to be +1 because chlorine is -1. Now chlorine is -1 over here, and over here it's -1 as well. There's 2 of them, so 2 times -1 is an overall negative charge of -2, which makes this zinc here a +2. Now keep in mind, zinc can have different charges because it's a transition metal. So whenever you see a transition metal, in order to sign its charge, remember its charge is usually in Roman numerals, you have to look at the non-metal portion. And what is that total non-metal portion? Is -2. There's only 1 zinc, so that would have to be a +2 because it overall has to total 0. Now, I look at the changes. So one of those elements is being oxidized and one of them is being reduced. So I match them up and I draw so I find my zinc and I draw my zinc to my zinc. and I draw my silver to my silver. Just like that. And so when I see plus 1 to 0, well, if you go from a plus 1 to 0, what if you had $1 and then you had none? Would you call that reduce? Yeah, so that's a reduction. So this is reduction. And then the other one would have to be oxidation. And I always just check, is it increasing in oxidation state? 0 to plus 2? Yeah, when you go from 0 to plus 2, that's an increase. So I always sign the reduction first because it's easier for me to memorize. The plus 1 to 0 is reducing, reduction. Okay, so that's that problem. Now go on to the next equation. Chemical reaction. Once again, we find the elements by themselves in the free state. We have oxygen that's going to get 0. And then over here, oxygen gets a minus 2 because it's in a compound and it's a group 6A, minus 2. And then I find my nitrogen, which is 0. And then over here, and this ammonia is kind of weird because you put a minus, it's a minus 3. It's very rare to actually write your negative charge first, right? But anyway, hydrogen, because hydrogen, when you're signing oxidation states, is always a plus 1. So it stays the same, so we don't worry about that one. So now we're going to match up the elements. So nitrogens, we're going to match them up. Nitrogen on the reactant side with nitrogen on the product side. And then we got oxygen on the reactant side with oxygen on the product side. Now remember, I like to do reduction, so I see a 0 to minus 2. And I know if I have $0 in my bank account, and now I have minus 2, I know that's a reduction. So that's a reduction in numbers, and that's a reduction. So oxygen is being reduced, and nitrogen is being oxidized. And then I double check it. And really, what are we going from? A negative 3 to a 0. So that is in fact being oxidized. Doing the same thing to the last equation. Aluminum is 0. And this aluminum here, well, I always have to look and say, okay, oxygen here is a negative 2, and there's 3 of them, so that makes my non-metal side negative 6. Aluminum needs to be, this cation side needs to be plus 6, if that's minus 6, and we have 2 because of the subscript 2. So plus 6 divided by 2 is plus 3 for aluminum. And then I do that with iron. Iron by itself, its element is 0. Iron over here, I do the same thing with, it's a transition metal, so I first look at the anion and say 3 times negative 2 is a negative 6. And iron, we need a plus 6, and we have 2. So plus 6 divided by 2 is a plus 3. And then I match them up, my iron with my iron on the reactant side with the product side, and my aluminum on the reactant side and product side. I like to look for my reduction. So a plus 3 to 0, iron is being reduced. So iron is being reduced, and aluminum is going from 0 to plus 3, and this is being oxidized, and that is an increase. Okay. Next problem. So 4.4-1 is a problem that I will look for in your recitation submission. This one should be easy after knowing your rules on page, this is 4-2. After learning your rules on page 177. And all it's asking is for you to determine the oxidation state of each. Well, nitrogen is its elemental state. It's actually nitrogen diatomic, so it's going to be 0. Lead, there it is. It's plus 2 because it's an ion. It's telling you plus 2. Carbon, well, by oxidations, we have to do a +1 for hydrogen, and there's 4, so that's +4. So carbon is -4 in this oxidation state. Here we have iron. Iron's a transition metal, so 3 times -2 for our oxygen is a -6. That means iron needs to be +6 divided by 2, because that's your subscript. You have 2 irons, so iron is going to be a +3. Silver and silver oxide. Well, based on our rules, oxygen always gets a -2, and so we need, on the cation side, we need a +2, so this overall charge of silver oxide would equal 0, and our subscript 2, if we take +2 divided by 2, that means silver oxidation state will be a +1. On to the next problem. Now we're doing stoichiometry. This is problem 4-3. 4-3. Okay, so the key here is you have a balanced equation. And I always check to make sure my equation's balanced. Okay, we have 2 aluminum, 2 aluminum. We have 6 hydrogens. We have 6 hydrogens. We have 3 sulfurs. We have 3 sulfurs. We have 3 times 4 is 12 oxygens and 12 oxygens. So I'm like, okay, it's a balanced equation. Because it doesn't do you any good to even, you're not going to get the right answer without a balanced equation. So if sometimes you have to write the equation, you're going to have to balance it. Now, we read the question, how many grams of hydrogen will be produced from 87.5 grams of aluminum? So this is typically what you have, is you start with one substance and then you work your way to the other one. Now, you're given, which I've told you is usually the unit with the number. So in this case, you're given is 87.5 grams of aluminum. And basically your conversion factor plan is going to be from your given, which is going to be grams of aluminum, and you've got to convert this to moles of aluminum. The only way you can go from one substance or element to another substance or element is through this thing what we call a mole-to-mole bridge. So if you want to go from a mole to aluminum, you can go from mole to aluminum to mole to hydrogen. That's the only time you can change the actual element or compound on your reaction bracket. And to figure out where these numbers come from, well, let's look. Where you go from gram to mole, this is molar mass. And where do you get molar mass? So for 1 mole, you're going to have so many grams of aluminum. Where does this number come from? That's right, it comes from the periodic table. We learned that last chapter. Well, to go from mole to mole, to figure out how many moles of aluminum equal moles of hydrogen, you have to look at, this is important, your balanced equation, and you're looking at your coefficients. Coefficients are the big number, not subscripts. Those are little numbers, so don't look at the subscripts. So if you look here, for 2 moles of aluminum, you get 3 moles of hydrogen. That is going to be your conversion factor that you're going to need. So that's why you have to have the balanced equation. And then once you go from mole of hydrogen, we're no longer into aluminum. We're in mole of hydrogen. We can go to gram of hydrogen. And once again, we do that by molar mass. And that's on the periodic table. So that's our conversion factor plan. Let's put it into action. So 87.5 grams of aluminum over 1. I think I need more space. Let's go down here a little bit further. 87.5 grams of aluminum over 1. And then I'm going to look at the molar mass on the periodic table, and I see 26.98 grams of aluminum for 1 mole of aluminum. And for a mole of aluminum, I can now go into a mole of hydrogen, because I can do that. And right here we looked at the periodic table, or the coefficients, the balanced equation, and I put 2 with aluminum and 3 with hydrogen coefficients. And the question asks for how many grams of hydrogen, so I can do molar mass for 1 mole of hydrogen. Molar mass always has a 1 with the mole. 1 with the mole. Molar mass. And on the periodic table, I see for H2, I need 2.016 grams of hydrogen. And that's from the periodic table. If I take 87.5 divided by 26.98 times 3 divided by 2 times 2.016, I get 4.90 grams of hydrogen. And I know I need 3 significant figures because we have 3 significant figures in our given. The next stoichiometry problem is problem 4-4. This is talking about glucose. C6H12O6 is an energy source of the body. We have our balanced equation. This is what we do every day. Our bodies are very efficient at breathing in oxygen, metabolizing sugar, and then we exhale carbon dioxide and we give off water. So we need to calculate the number of grams of oxygen required to convert 48.0 grams of glucose to CO2 and water. So for this one, we are going from, what's our conversion factor plan? We're going from grams of glucose, C6H12O6, and we got to go straight into moles. We got to go moles of glucose because we can't change substances unless we're in the moles. And it wants the number of grams of oxygen. So it wants oxygen. You see, we read the question, number of grams of oxygen. So where are we going to go? We're going to go from moles of glucose to moles of oxygen, and then we can go to grams of oxygen. So to go from grams to moles, we're going to use the periodic table for molar mass, but to go from moles of glucose to moles of oxygen, we're going to look at the coefficients, and we see that there's no number in front of glucose, so that's going to be 1, and what's the number in front of oxygen? 6. So our conversion factor for that will be for 1 mole of glucose that equals 6 moles of oxygen. And that'll be our conversion factor. Now, this is whenever you get a big compound like this too, because we're going to have to use the molar mass, you need to go ahead and calculate the molar mass of glucose, C6H12O6. So if you look at your periodic table, you'll see 6 times 12.011 for carbon, plus hydrogen, which is 12, we got 12 of them, times 1.008, plus we have 6 oxygen, which is 6 times 16.00. If you add that up, the molar mass ends up being 180.15 grams of C6H12O6 for 1 mole of C6H12O6. So let's go ahead and work this at the bottom here. So I'll call this number 1, and we'll work number 1 right here. So it says calculate the grams of oxygen required to convert 48 grams of glucose. So let's go ahead and do this. So we have 48.0 grams of glucose, C6H12O6 over 1. And then we just calculated the molar mass of glucose, 180.15 grams of glucose per 1 mole of glucose. Now we're going to go right here, moles of glucose to moles of oxygen. We can change substances, right? So we don't want moles of glucose. We're going to put that on the bottom. Moles of glucose to mole of oxygen. And we looked at our coefficients, and we see that there's an understood 1 with glucose, and then there's a big number 6 in front of oxygen in our balanced equation. So we put 6 with the oxygen, but our question is asking for grams. So we're going to use molar mass of oxygen. So for 1 mole of oxygen, we get 32.0 grams of oxygen from the periodic table. We take that times 2. So when we plug this in our calculators, we plug in 48.0 divided by 180.15 times 6 times 36. 36? Ooh. That means, it's 32. 16, 32. So let's see what that is. 48 divided by 180.15 times 6 times 32. And your answer should be 51.2 grams of oxygen. Okay? So that is problem number 1. And then problem number 2, call this one number 2. We'll work down here. Calculate the number of grams of CO2 produced. So CO2 is 6 here. So we could just we could go from grams of oxygen, or we can go from grams of glucose. If I was doing this on a test, I would just go with grams of glucose, because what if that other problem was wrong, right? 48 grams of C6H12O6, this is our given. And then for 180.5 grams of C6H12O6 in 1 mole of glucose, H12O6, and for 1 mole of C6H12O6, we have 6 moles of CO2. Let's go back and look in case see the number 6. This is understood 1. We get that from our balanced equation. And then we need to use the molar mass because the question asks for grams of CO2. So for 1 mole of CO2, we have to use this molar mass, which we get from the periodic table. 1 carbon plus 2 oxygen should total 44.01 grams of CO2 per 1 mole. And then we type that in our calculator. 48 divided by 180.15 times 6 times 44.0. Our answer should be 70.4 grams of CO2 produced. The next problem is problem 4-5. This is a neutralization reaction. So you need to recognize these different types of reactions. Neutralization reactions are usually a strong acid plus a base. Anytime you add an acid and a base, you get water and you get a salt. And a salt is considered an ionic compound. And a good example is sodium chloride, but that's not the only salt. So an ionic compound is considered a salt. It breaks up in aqueous solutions into its plus and minus charges. So this will break up into barium 2 plus and NO3 minus. There will actually be two nitrates. Water will not break up. That's why it's an L. And but the acid will dissociate in nitric acid will associate in H plus NO3 minus. Also barium hydroxide will break up into barium 2 plus, and this will be 2OH minus. So those are aqueous solutions and they break up in solution, which is water. So that's what a neutralization does. An acid plus a base equals a water plus salt. Now I like to check to make sure, are they balanced? We got four hydrogens on both sides. Nitrogen, we have two nitrogens on both sides. We have one barium. I think we're good. Okay, so we can read the problem. The problem Okay, this problem is 4-6, and I want you to go ahead and change the potassium sulfate or sulfite to potassium sulfate, because that way it'll match up with your rules here. Table, that's really bad, 4.1 that you have to memorize on page 161, your solubility rules. You don't have sulfite, but you do have sulfate. And so let's start working these. So the first thing you do is you write these down with their charges. So silver nitrate, that's a +1, and this polyatomic anion you memorize was -1. And potassium, you got 2 potassiums, they're +1, and sulfate is SO4 2-. And so your last chapter you were supposed to memorize your polyatomic anions and their charges. Now what's going to happen here is you got to write the reaction. So silver nitrate, and you're going to have to fill in, this is aqueous, they've already given it to you, with potassium sulfate. Now this means when you put aqueous that what's actually in solution are these ions and their different charges. That's what's actually in solution. They're broken up. When you are, I'm doing my double-headed arrow here because it's an equilibrium, what you're trying to do is a precipitation reaction. So what happens is when potassium pairs up now not with sulfate, but when potassium bumps in to nitrate and nitrate bumps into potassium, what happens? Well, you get potassium nitrate, and that's a -1 and a +1 charge, so this is what that compound looks like. When that happens, you have to say, is that soluble? And that's why you have to memorize the solubility tables in 4.1. And when you recognize that, oh, nitrates are generally soluble, there's no exceptions. I think the videos are really good about this too. So whenever you see nitrate, there's no exceptions. So whenever you see nitrate, that's going to be soluble. So you can go ahead and write potassium nitrate aqueous, because that's going to be soluble. There's no exceptions. Now, this is kind of like a do-si-do. All you got to do is remember to switch places. So silver is going to switch places with the cation potassium. So we've already switched places here, and now so silver is going to switch partners with sulfate, and then what does that compound look like? Well, silver is a +1, sulfate is SO4 2-. When we combine these, like we did last chapter, to figure out what the subscripts are going to be, it's going to be silver 2, sulfate 1. And now we don't know what to put here, right? Is it going to be a solid, which means it's insoluble, or are we going to put aqueous, which means it's soluble? That's where we have to have our rules memorized. And this is actually going to go over here. I'm going to really go off the page here. Plus silver sulfate. Put our little 2 there. And what is this going to be? Well, what's our rules say about sulfates? So I'll give you time to look at that table. Page 161, if you haven't memorized it. Sulfates are generally soluble. So sulfates are usually soluble, except when paired with strontium, barium, lead, silver. Okay, so that tells you right there this is going to be a solid, and when we write that reaction, we put a solid here. So this is solid. What is the net ionic equation, including phases, for the reaction of silver nitrate with potassium sulfate? Now, That is your net equation, but that's not your net ionic. So to write your net ionic, come down here, your net ionic equation, you have to cancel out your spectator ions. So the best thing to do is where we see aqueous, you break them up into their charges. So the first one breaks up into Ag plus 1 plus, and you keep aqueous, plus nitrate, NO3, 1 minus, keep aqueous, plus, this is 2 potassium plus 1s because the subscript, 2, that's aqueous, plus 1 sulfate, 2 minus, aqueous, our double-headed arrow. Okay, we have aqueous here, so we're going to break this up into potassium plus, it's aqueous, plus NO3 minus aqueous, because of the aqueous. And then we have, we don't break that one up, okay, because it's solid. So we're just going to go plus silver sulfate solid. Now, any ion or cation that you see on the reactant side and also the product side, oh, did you see what I did that was wrong? Before you actually go to make your net ionic equation, you need to balance this equation. So let's balance this real quick. How many silvers do we have? 1 silver and 2 silvers. So we're going to have to put a big 2. Big 2 in front of the silver nitrate. Now we have 2 nitrates, and we need to put a big 2 in front of the nitrates on the reactant side, on the product side, and now we have 2 potassiums and 1 sulfate. So we need to make sure we put a 2 here for 2 silvers, and here we have 2 nitrates and 2 nitrates here. So now it's balanced. Apologize for that. Okay, now we're going to cancel out anything we see on both sides. So we don't see a silver plus ion, cation on the product side. We also do not see a nitrate anion. Actually, that's not true. We do. There's 2 there and there's 2 there. So we're crossing out our spectator ions. These are called spectator ions. Here we have potassium on both sides. We're going to cancel that out. Do you see a sulfate anion? No. So we're going to keep that. And then we're going to rewrite what's kept. So we'll do 2 silver plus 1. Keep your phases when you're writing these. Plus sulfate 2 minus aqueous goes to silver sulfate solid. And that is your net ionic equation. This is problem 4-7. Complete and balance the molecular equation including phases for the reactions. So this is more precipitation reactions, which you'll have to memorize your table. I'll write it again. Table 4.1, page 161. And when you look at that table, let's do our do-si-do. So first of all, we're going to break iron. Now nitrate is a polyatomic anion that you needed to remember. That's -1. There's 3 of them, so that is -3 charge. That means iron's going to be a 3 plus because it's a transition metal. Here, OH is your polyatomic anion. You memorize that was -1. And so that makes, and lithium's going to be +1 anyway, right? Because it's group 1A. So those are your charges. Now what's going to happen is right now iron is with nitrate, but now iron is going to go in aqueous solution and bump into hydroxide. And what would that compound be? We figure out what our subscripts are to give an overall 0. So there's one iron. We have a polyatomic anion, so we're going to put parentheses, and there's going to be 3 of those, right? So the question is, right there, are we going to put solid or are we going to put aqueous? So we'll put this here, and we'll just leave that blank for now. And then our next lithium is going to bump into the nitrate, and it's going to form lithium nitrate. And since nitrate has a -1 and lithium has a +1, that is going to be just 1 lithium and 1 nitrate. Now we're going to have to decide whether it's solid or aqueous here as well. But before we do this, let's balance the equation. 1 iron, 1 iron. We have 3 hydroxides. So we need 3 hydroxides here. We're balancing this. We have 3 nitrates, so we need a big 3 in front of the nitrates here. We have 3 lithiums. So let's just double check. 1 iron, 3 hydroxides, 3 nitrates, and 3 lithiums. Okay, so now it's balanced. Now, what's our solubility rules? For hydroxides, what's it say? Hydroxides are generally insoluble, except when paired with lithium, the same ones, you know, the usual suspects here, lithium, sodium, potassium, and ammonium. So what about iron? Yeah, so it's insoluble. It's going to be S. And we know that nitrates, there are no exceptions. They are aqueous. They're always soluble. So that is our molecular completed balanced equation. But here we want the net ionic, including the phases. So we just break them up into their charges, and then we're going to cross out the spectator ions. So we have iron 3 plus, I'll put this down here, aqueous, plus 3 nitrates, aqueous, plus 3 lithium, aqueous, plus 3 hydroxides, and this goes to, here we have a solid, okay? So that's another reason why you always write these phases down too, because then you're like, oh, I can't break up a solid. That's the whole purpose. So that's going to stay a solid. And then we break up here. These are aqueous, so 3 lithium ions, aqueous, plus 3 NO3, 1 minus, aqueous. Now we're going to cross out our spectator ions. Do we see iron on both sides? No. So we're going to end up keeping that. Nitrate, yeah, that's a spectator ion. Lithium, yep, spectator ion. What about hydroxyl? The hydroxide, that's going to stay. So then we rewrite this for our net ionic equation. We would write Fe 3 plus, including phases, aqueous, plus 3OH minus aqueous yields, I think in this case actually it would be, when you're doing this one, it's irreversible. Iron hydroxide. So it's iron 3 hydroxide, and that's your net ionic equation. Next problem is 4-8. We have lots of problems in this chapter. Precipitation reactions. We're still writing net ionic equations. So for each reaction, identify the precipitate or lack thereof. Alright, So the nice thing is we have the reactions already combined, right? Calcium combined with carbonate, potassium combined with chloride, and it is balanced, right? Yes, it's balanced. So if you check that, so your goal is to figure out in these little parentheses, is it going to be S or is it going to be AQ, soluble? So let's look, and that's applying your solubility rules that we talked about. So carbonate. So look at carbonate. So carbonate here, carbonate CO3 2 minus. What do the rules say? This is in table 4.1, page 161. It says it's insoluble except when with the same ones: lithium, sodium, potassium, and ammonia. So calcium is not lithium, sodium, potassium, or ammonia. So therefore it's going to be insoluble. It gets an S. And then potassium chloride is potassium is soluble, no exception. So K plus, it's always soluble, no exception. So that will be aqueous. The next problem, they've already paired up the different cations with the anions and balanced the equation. So our goal is to figure out what would go in these parentheses. So we have to apply our memorization from table 4.1. And so the first thing we're going to look at is the sulfate. And what is the rule on sulfate? They're generally soluble. Except when paired with, these are all 2 plus charges, which I think is interesting: strontium, barium, lead, this is only 1, silver, it's a 1 plus charge, and calcium, 2 plus. So is that going to be soluble? Yes, that's going to be soluble because iron is not any of these cations. And then we look at the next reaction, or the next compound, and ammonium is in the none exception. So that's going to be aqueous as well. In that case, there is no precipitation if you mix those reagents together. Next problem is 4-9. 4-9 is a limiting reagent problem. How do you recognize that's a limiting reagent problem? Well, yes, it says limiting reagent, right? But you're not going to always know that. So we have 2 reagent amounts. Silver nitrate, 126.65 grams of silver nitrate is allowed to react completely with a solution containing 18.23 grams of lithium chloride. This is also one of your problems that are due. So I'll just, for recitation. How many grams of solid precipitate will be formed? So the first thing you're going to have to do is you're going to have to write a balanced equation from that information. So everything we've applied so far, we're going to have to do that. So let's do that. Silver nitrate. Silver nitrate is AgNO3. And since those are both plus 1 and minus 1, then we don't have to worry about the subscripts. Plus, and we're adding lithium chloride. Lithium chloride. Lithium is plus 1 and chloride's minus 1, so once again we don't have to worry about it. And then what's going to happen? Silver is going to combine with the chloride. We don't know what's going to go in that parentheses yet. And lithium is going to combine with the nitrate. And that is really an ugly nitrate. Okay. Lithium NO3. They're both +1 and -1. And this is, we definitely know this one's aqueous, right? Because nitrate is always going to be soluble. Silver chloride. What's the rules on your table? Okay. Do we have the rules? I wrote them down. Let's see. Yeah, so silver chloride. I think you have it with your highlight. Okay, I'm back, and basically what I want to say is to figure out silver nitrate, it's easy, it's just to take your excess. So 53.6 grams of silver nitrate is left over. And then we're going to convert that to moles because it asks for moles in the problem. So silver nitrate molar mass on the periodic table is 169.88 grams per 1 mole of silver nitrate. And when you put that in your calculator, because also for 1 mole of silver nitrate, because there's no subscripts, you have 1 mole of silver ion. You put that in your periodic table, or you put that in your calculator. It should be, here, I'll do it real quick. My notes have gotten kind of messy. 53.6 divided by 169.88, and that's 0.316 mole of silver ion, and then you would also have the same 0.316 mole of the nitrate, because for 1 mole of silver nitrate you're going to have, in that case, 1 mole of nitrate. So you're going to have the same amount. And that's how to work that problem. Next problem is 4-10. And you'll find that these limiting reactant problems are long, especially combined with precipitation problems. But it's good to know, and most of the problems on the exam will be broken up into pieces of this. So you'll just, so by being able to work the entire problem, maybe would be worth 4 or 5 questions on the exam. Okay, so they're worth doing. Okay, if a solution containing 85.331 grams of mercury 2 chlorate is allowed to react completely with a solution containing 12.026 grams of sodium sulfite, how many grams of solid precipitate would be formed? This is just like the last one, right? And we have to write the balanced equation by applying our precipitation rules. And then we need to figure out who's the limiting reagent, because we're also given the amounts, the grams for each reactant. So the first thing we need to do is write these down. So this is chlorate. You should have memorized chlorate was one of your polyatomic anions, and chlorate is ClO3 1 minus. So mercury 2 chlorate would be Hg, and we need 2 of these, so it's ClO3 with a subscript 2. And this is going to be aqueous. And we add that with sodium sulfide. So sodium sulfide is S2 minus, so it's going to take 2 sodiums for 1 sulfide. That's going to be aqueous. And then we kind of do our do-si-do, right? Mercury is going to combine with the sulfide. And since that's mercury H2 plus, sulfide's 2 minus, they work out. We don't have to worry about that. And we're going to have to try to figure out what to put in that parentheses for, is it either going to be aqueous or solid. And so then sodium's going to combine with chlorate, and sodium's a +1 and chlorate is a -1, so that works out fine. And once again, we're going to have to figure out what to put there. So looking at our solubility rules, what's our solubility rules? Decide. S2 minus, so sulfide, S2 minus is insoluble with unless it's with the usual 4, right? Lithium plus, sodium plus, potassium plus, and ammonium. Okay, so mercury is none of those, so it is going to be insoluble. It is going to be solid. It's going to be, that's the product we care about. And once here we have sodium, Sodium is one of those 4, so this is going to be aqueous. So we can put aqueous there. And we need to balance our equation. We have 1 mercury. We have 2 chlorates. So we need to put a big 2 in front of the sodium chlorate over there. We have 2 sodiums, 1 sulfur. So by adding that 2, we have a balanced equation. We have to have a balanced equation in order to do stoichiometry because we're changing from one substance to the next. How many grams of solid precipitate will be formed? Well, we have to figure out which one's our limiting reagent. So for each one of these, we're going to take the grams of the reactant and we're going to convert it to moles of the reactant. And then we're going to convert that to moles of the product, silver sulfide. And we're going to figure out the least number of moles. And then when we do that, that's our limiting reagent. And from there, we work from the limiting reagent to figure out grams of product. Okay, so we're going to do this with both mercury chlorate, and we're going to do this with our sodium sulfide. So let's start. 85.331 grams of mercury chlorate over 1. And then we got to get it into moles, so we got to do molar mass. So grams of mercury chlorate for 1 mole of mercury chlorate. So what is that? If you add on the periodic table, you add 2 chlorines, 6 oxygens, 1 mercury, you should get 367.49 grams. And then we look at the periodic table and we see for 1 mole of mercury chlorate, we have how many moles of product? 1 mole of mercury sulfide. And we put that in our calculator. It gives us 0.232 mole of product, mercury sulfide. Now we have to do the same thing with our other reactant. So 12.026 grams of sodium sulfide over 1. Molar mass 78.07 grams of sodium sulfide and 1 mole of sodium sulfide. We look at the periodic table for 1 mole of sodium sulfide. These are our coefficients. We have 1 mole of mercury sulfide. So when we put that in our calculator, our answer is 0.154 mole of mercury sulfide. When we compare these numbers, so the mercury chlorate generates 0.232 moles of mercury sulfide, and the sodium sulfide produces 0.15 mole of mercury sulfide. So which is our limiting reagent? That's right. So sodium sulfide is our limiting reagent. So basically we're going to take 0.154 moles of mercury sulfide over 1, and we're going to use molar mass. So for 1 mole of mercury sulfide, we look at the periodic table. I think mercury is very heavy, like 200. And then sulfur is 32, so we end up getting 232.66 grams of mercury sulfide. And we multiply that with 0.154, we get 35.8 grams of mercury sulfide formed. So that is your answer to your first question of this problem. Your second question of this problem was how many grams of the reactant in excess will remain after the reaction. So remember, we take what we have, we get that from the problem, for our excess minus what was used equals our excess. So what we have, and they want to know how many grams. So what we have is 85.331 grams of mercury chlorate. And we got that in the problem. That was our given. Now we're going to minus what was used. So how do we figure out what is used? Well, we start with our limiting reagent right here. And so we're going to take 0.154 mole of our product, mercury sulfide, over 1, and we're going to convert the mole of mercury sulfide to mole of mercury chlorate. And so if you look at the balanced equation that we wrote in the very beginning, you would see that for 1 mole of mercury sulfide, we have 1 mole of mercury per chlorate, or just chlorate, sorry, and that's going to be 0.154 mole of mercury chlorate that was used. So when we take this and subtract it from what we have, so, what do we need to do? That's right, we need to convert this to grams. So let's go on. 0.154 mole of mercury chlorate, and we use molar mass for 1 mole of mercury chlorate. We have 367.49 grams of mercury chlorate. And when you put that in your calculator, you should get, keep that there, you should get 56.59 grams of mercury chlorate used. Okay, so that's what's used. So we will subtract 56.59 grams to give us an excess of 28.74 grams of mercury chlorate. Okay, we have another limiting reagent problem. So this is problem 4-11. And I do believe 4-11 is one of your problems that's required. So pure magnesium metal is found as ribbons and can easily burn in the presence of oxygen. When 4.88 grams of magnesium ribbon burns with 8.92 grams of oxygen, a bright white light and powdery product are formed. Okay, so the first thing they're asking is, write what is the balanced equation for the reaction. Include the physical states of matter. So the magnesium is a ribbon, that's a solid, and it's an element. And you're reacting with oxygen, which is gas in the air, and that is going to make magnesium oxide. And magnesium is a 2 plus, well, not in there, but in an element it's 0, right? But when it's in a compound it's 2 plus, and oxygen's 2 minus, so we're good. And that is a white powdery product, so that product means it's going to be a solid. And we need to put a 2 in front of magnesium oxide because we have 2 oxygens in the reactant, and then that means we need a big 2 in front of magnesium. So we have the balanced equation with our physical states. What is the limiting reagent? So we're going to have to solve for the limiting reagent like we always do, and we're going to take the amounts. So this is for the limiting reagents. We're going to take 4.88 grams of magnesium, and we're going to look at the periodic table, and we're going to see that 24.31 grams of magnesium equals 1 mole of magnesium. excuse me. And for looking at our periodic table, 2 moles of magnesium form 2 moles of magnesium oxide. And when you put that in your calculator, you get 0.201 mole of magnesium oxide. Now we have to do the same thing with the other reactant, and then we'll compare the two. So the other reactant, we started with 8.92 grams of oxygen. Put that over 1. And the periodic table, 16 plus 16 is 32.00 grams of oxygen for 1 mole of oxygen. And looking at the balanced equation, for 1 mole of oxygen, we get 2 moles of product, magnesium oxide. So there's a 1 there because there's nothing there, and then there's a 2. When we put that in our calculator, we get 0.558 moles of magnesium oxides. So what's limiting here? Is it the magnesium ribbon, or is it the oxygen gas in the air? It is the magnesium ribbon because 0.201 is less than 0.558. So what is the limiting reagent? Magnesium. The next question. The percent yield for the reaction is 84.7%. How many grams of product were recovered? It's good to take this 84.7%. We're going to make it a conversion factor. So we're going to say 84.7 grams of product, magnesium oxide, over 100 grams of magnesium oxide. So the percent yield, so that we're going to make that a conversion factor, how many grams of product were recovered. So basically, you're going to have to start with your limiting reagent, because that's the most you can make. So you make 0.201 mole of magnesium oxide over 1. And we got to get into grams, because this is our conversion factor, grams. It's asking for grams. So we're going to use our molar mass. 1 mole of magnesium oxide equals, if you look at the periodic table, you'll see that that's 1 magnesium, 1 oxygen. Should be 40.3 grams magnesium oxide. And then we can use our conversion factor. For 100 grams of magnesium oxide, we get 84.7 grams of magnesium oxide. So if you put this in your calculator, the moles cancel, the grams cancel, but you get grams here. And this ends up being 6.86 grams of magnesium oxide. So that is your answer, 6.86 grams. Then the last question here is how many grams of the excess reactant remains? So they're asking about oxygen here. Once again, we apply the have minus used equals excess. Where do you find the have? Find the have in your starting problem. So you have, and it asks for grams of excess. So 8.92 grams of oxygen is what you have. Well, what you used, you want to start with your limiting reagent here. So you start with 0.201 mole of magnesium oxide. And we're going to convert that to moles. Magnesium oxide to moles of oxygen. And then we'll use the molar mass for 1 mole of oxygen. We get 32.0 grams of oxygen. And that's going to give us what we used. Where do we find the numbers to go here? From the balanced equation. In our balanced equation from earlier, 2 goes with magnesium oxide, 1 goes with oxygen. So when we take 0.201 divided by 2 times 32, we get 3.216 grams of oxygen. So what we're going to do is we're going to subtract from the 8.92 what we have minus 3.216 grams of oxygen, and that is going to give us an excess of 5.704 grams of oxygen. That should take care of 4-11. Another limiting reactant problem. See how many more we have? Okay, this is our last limiting reactant problem. Maybe. I don't know. I think we might have another one. Okay, 4-12. Cryolite gives you the formula. Sodium aluminum fluoride is an ore used for the production of aluminum that can be synthesized using aluminum oxide. And they give you the equation, but they said balance the equation. So to balance the equation, I like to do my little chart here. So I do my reactant, we just call this R, and our product. And then I list them. So we'll do aluminum, we'll do oxygen, sodium, and due to space, we'll come down here, reactant and product, and we have hydrogen and fluorine. So we have the reactant side and the product side. So here we have 2 aluminum on the reactant side, and we have 1 aluminum on the product side. For oxygen, we have 4 on the reactant side, and we have 1 on the product side. Sodium, we have 1 sodium on the reactant side. We have 3 sodium on the product side. For hydrogen, we have 2 on the reactant side, and we have 2 on the product side. Fluorine, we have 1 on the fluorine side, and on the reactant side, and 6 on the product side. Now, the first elements to do are aluminum, sodium, and then fluorine. You do the hydrogen, oxygen last. So what number can I multiply a big coefficient through on which side of the equation to get the aluminum to equal? That's right. So if I put a 2 in front of the sodium cryolite compound, then I will have 2 aluminum. So now I have 2 aluminum. But that changes everything, right? So then we got to recalculate. So the sodium now is 6, and our fluorine, 2 times 6, would be 12. But we are fine with our aluminum. So now we're going to skip over the oxygen, and we're going to go to sodium. And we have 1 sodium on the reactant side, and we have 6 sodiums on the product side. So what number can we put in front of the sodium to get that to work out? That's right. So we can put a 6 in front of the sodium. So if we put a 6 in front of the sodium, that changes our sodium to 6, and our oxygen now is 6, 7, 8, 9, and our hydrogen count changes to 6, 7. So we fixed that, and the question is there sodium equal? Yes. And our aluminum still equals. So the next element we're going to is fluorine. So we have 12 fluorines on the product side. We only have 1 fluorine on the reactant side. So what number do we put? Yeah, we'll put a big 12 in front of HF. And then that's going to make the fluorine equal. But it changes our hydrogen count to 12 plus 6 is 18. So this is going to be 18 hydrogens. Now the next thing we want to do is go to our oxygen. And we have 9 oxygen on our reactant side, and we have only 1 oxygen on our product side. So if we multiply, put a big 9 in front of the water, now we'll have 9 oxygens on our product side. And the oxygen's equal, but we have to fix here. Now we have 9 times 2 is 18. We have 18 hydrogens on our product side. Oh, well, look at that. 18 and 18, so the hydrogens work out. So that's our balanced equation. We have a 6 in front of the sodium hydroxide, 12 in front of HF, 2 in front of acrylite, and a 9 in front of water. Okay, so let's go on to the next question, which is, if 16.7 kilograms of aluminum oxide, 51.4 kilograms of sodium hydroxide, and 51.4 kilograms of HF react completely, how many kilograms of acrylite will be produced? This means we have to figure out our limiting reactant, and now instead of 2, we have 3. So we're going to have to take 16.7 kilograms of aluminum oxide over 1, and we got to get from kilograms to grams, so you need to have memorized for 1 kilogram you have 1,000 grams, because we got to use molar mass. And what's the molar mass of a aluminum oxide? Would be 101.96 grams of aluminum oxide for 1 mole of aluminum oxide. We want the product, right? Which is the acrylite. So then look at your balanced equation. 6 moles of aluminum oxide for, not 6 moles, what is it? 1 mole. Because there's no number in front of there, equals 2 moles of, we'll just write acrylite. Okay, so when you put that in your calculator, you should get 327.6 mole. We'll just call that product. And we have to do this with the other 2 reagents. So we're going to do 51.4 kilogram of sodium hydroxide. And then for 1 kilogram, we have 1,000 grams. And what's molar mass of sodium hydroxide? Sodium hydroxide is 40. 40 grams sodium hydroxide and 1 mole of sodium hydroxide. And look at the balanced equation for 6 moles of sodium hydroxide. How many moles of product? 2 moles of product. And when you put this in your calculator, you will get 428.3 mole of product. So we know this is not our limiting reagent, isn't it? And what's the last one? The other one's 51.4 as well. 51.4 kilograms of HF over 1 kilogram per 1,000 gram. HF's molecular mass is 20 grams HF for 1 mole of HF. And looking at our balanced equation, for 12 moles of HF, we have 2 moles of product. And when you put this in your calculator, you should get 428.3 mole of product. So, your limiting reagent then is your aluminum oxide. And it asks how many kilograms of cryolite will be produced. So you're just basically going to take the 0. You're going to take your limiting reagent, 327.6 mole of cryolite over 1, and for 1 mole of cryolite, we look at the periodic table. You're going to have to add that up. You're going to have to add the formula, which is 3 sodium, 1 aluminum, 6 fluorine, and that will give you a molar mass of 209.98 grams. I'm going to put cry. Okay, is that okay? Cry? But it wants kilograms. So then for 1,000 grams, we have 1 kilogram. So when you put that in your calculator, you should have the answer. I'm going to put it right here. 68.8 kilograms. 68.8 kilograms. Which reactants will be in excess? Let's just write those down. What are they? Sodium hydroxide and HF, hydrofluoric acid. What is the total mass of the excess reactants left over after the reaction is complete? Okay, so the last question. What is the total mass? You want to convert both to grams because you want to convert both to grams that are used. And then you're going to subtract that from the whole have minus used equals excess. So you're going to find the excess for each one, and then you're going to add those together. So when you start with this, you do 327.6 mole of cry. That's our product, right? And for 2 mole of cry, we're going to do sodium hydroxide first. 6 moles of sodium hydroxide. And we need grams. So now we take from 1 mole of sodium hydroxide equals its molar mass, 40.0 grams of sodium hydroxide. And when you add that in your calculator, you get 39,312 grams of sodium hydroxide used. You're actually going to have to convert this to kilograms, so that'll be 39.312 kilograms. So, because what did we have? We started with 51.4 kilograms, and we subtract 39.312 kilograms used. And when we do that, we get let me see, 51.4 minus 39.312, we get 12.088 kilograms of sodium hydroxide, and you do the same with the next one. So we take 327.6 mole of cryolite, and for 2 moles of the cryolite, we're going with HF, right? We get 12 moles of HF, and for 1 mole of HF we have 20 grams of HF. And then let's just go ahead and convert that to 1,000 grams of HF equals 1 kilogram of HF. So when you do that, ironically, it works out to be 39.312 kilograms. And this is used. And remember, you started with the same one, 51.4 kilograms minus that. So your excess really is 12.088 kilograms of sodium hydroxide plus 12.088 kilograms of HF. And that's going to give you 24.18 kilograms of the total mass of your excess reactants left over after your reaction is complete. Okay, that last one was a long problem. We are now on problem 413. It's a titration problem. I think your last chapter 4 lecture videos actually goes through good detail on how to do a titration. If you go in industry and work in quality control, you probably do titrations weekly. So it's good skill to know. In this reaction, it talks about the ions here. You got the sulfate. But then here, this is confusing for new chemists a lot of times. Here, this is actually the source of your sulfate ion is actually from here. So when you get 0.250 molar of sodium thiosulfate, that's the same thing as the thiosulfate in your reaction. And so remember when I told you when you see this 40 milliliters plus a concentration, what does that tell you? Well, you can convert the molarity into a conversion factor, and that will automatically give you moles of Na2AS2O3. And in this case, that in the written equation here is S2O3 2 minus. This is your net ionic equation, right? Because the spectator ions are canceled out. And it wants you to calculate the molarity of I3. So it wants the molarity. So remember, molarity will be moles of I3, iodide minus, over the liter of solution. Now, we know once we got a chemical equation, is it balanced? Yes, it's balanced. And we know that we can take this combination, 40 milliliters of 0.250 molarity, to give us the moles. And once we have the moles of your thiosulfate, we can figure out the moles of your I3. And then we're just going to divide that by the total amount of the solution that we have in our flask. So let's just start with getting our moles. So we take 40.0 milliliter, and this is of sodium 2S2O3, and then we need to, because this is 0.250 mole of Na2S2O3 in 1 liter of the solution, Na2S2O3. We need to get the milliliters into liters, so we're going to go 1,000 milliliters equals 1 liter. And then we're going to say for 1 liter, we have 0.250 mole of Na2S2O3. And then we're just going to go ahead and convert. We're going to look at the coefficients, because we know we can go from a mole of Na2S2O3 to mole of the question that we care about is I3. So look at the coefficients in the balanced equation. This one here has a 2, and this one here has an understood 1. So when we put that in our calculator, we get 0.005 mole of I3 minus. But the question wants molarity, so how much do we have? So it requires 40 mils of this solution to titrate 25 mils. So this needs to be over our total volume. Okay, so our total volume is going to be 40.0 milliliters plus 25.0 milliliters, and then we got to convert that, so 1,000 milliliters into 1 liter. So when we do that with our calculator, we get 0.005 divided by the total volume, which is 40 plus 25, and then we convert that, we get rid of our milliliters, so it's molarity. So we're going to take that times 1,000, and we get 0.07. I want 3 significant figures, 769 molarity. And so that is our answer. Okay, 414. This is your last problem. And if I'm looking at this correctly, this is a problem that's required. So let's do this. First, you need to write the balanced neutralization reaction between sulfuric acid and potassium hydroxide in aqueous solution. So these are both strong bases. So what happens is you get H2SO4 aqueous plus potassium hydroxide aqueous, and this is going to go to what all neutralization reactions with a strong acid and strong base, water, which is a liquid, it doesn't break up, water, and then we have a salt. So basically the salt came from the K+, the OH here made the water, and this H2 from the acid made the water. So the hydrogen proton from the acid made the water, and the OH minus from the base made the water. So the salt's going to come from this sulfate and the potassium. And so we have potassium, sulfate, and because we have one of those, we need 2, because we have a 2 minus here. And this is going to be an ionic compound, therefore a salt, and it's aqueous. Now we need to balance this equation. So we have, let's look at sulfate, 1 sulfate, 1 sulfate. 2 potassiums, okay, we need a 2 there for potassium. We have 4, 5, 6 oxygen, so let's put a 6 here. No, that's not right. Let's not do that. Okay, so let's not include our sulfate. Okay, so we have 2 oxygens, so we're going to put a 2 there. And that's 2 oxygen. We have 4 hydrogens, and we have 4 hydrogens over here. 1, 2, 3, 4. So that should be balanced. And then once we have the balanced neutralization reaction, we can go to the next question. Immediately I see 0.950 liters of a molarity. What does that tell me? It tells me I can get moles of H2SO4. And it's reacted with 0.9 liters of this molarity, which I can get moles of KOH. This also tells me, wow, I have moles or amounts of both reactants. So that tells me that this is actually a limiting reagent problem. What concentration of sulfuric acid remains after neutralization? So I'm going to have to find my limiting reagent. You always have to find your limiting reagent unless it says which one it is. And then if it says which one it is, you just work with that one. But so we're going to have to convert to moles of, in this case, sulfuric acid to moles of a product. And we can just pick whatever product we want here. Let's just pick water because we know water is really easy, right? 18.01 grams per mole. Or did I actually went with the other one, so let's just go with the other one. It doesn't matter here. So, anyway, so if you calculate the molar mass, this is going to be our product, and I'll just write product. Molar mass for this potassium sulfate is, what is it? Actually, we don't need it. We don't need it because we're just going to go to moles. Sorry about that. Okay, so let's just start this. So we have 0.950 liter of H2SO4, sulfuric acid. And for 1 liter, remember this we make molarity we make into a conversion factor, 0.490 moles of H2SO4. And then we're going to use our balanced equation, and we see that 1 mole of H2SO4 equals 1 mole of K2SO4. And when we put that in our calculator, we get 0.4655 mole of product. We'll just write product because we're going the same product. Doing the same thing here. For the KOH, we're going to do 0.900 liters of KOH. And for 1 liter, we have 0.200 moles of KOH. And looking at our balanced equation for 2 moles, our coefficient of KOH, we have 1 mole of product, K2SO4. And when we put that in our calculator, we get 0.09 mole of product. Okay. Which one is the limiting reagent? Yes. It's the KOH. So we're going to work from the KOH. What concentration of sulfuric acid remains after neutralization? So we're going to start with 0.09 mole of K2SO4 over 1. And we're going to convert it to moles of sulfuric acid because it's acid and sulfuric acid. So for 1 mole of K2SO4, we have 1 mole of H2SO4. And we get that from the coefficients in the balanced equation. So we have 0.09 mole of H2SO4 used because it's asking what remains after neutralization. Well, what do? We have minus used equals excess. So the have would be right here, which we're going to have to go back and get. What we have is 0.950 liters of sulfuric acid, and for 1 liter we have 0.490 moles, and that equals 0.4655 mole of sulfuric acid. So when we take 0.4655 minus 0.09, we get, put that in my calculator, 0.4655 minus 0.09, we get 0.3755 mole of sulfuric acid left over, but the question's asking for concentration. What do we do when it asks for concentration? We need the mole of sulfuric acid over the total volume, liter of solution. So we do have the moles here, 0.3755 mole of sulfuric acid, but what's our total volume? And basically we have added 0.950 liters of sulfuric acid, and we also added 0.900 liters of potassium hydroxide. So we're just going to take that 0.3755 and we're going to divide that by the sum of 0.950 and 0.9 to give us an answer of 0.203 molar sulfuric acid. You see, and that's exactly what I got. Okay, and that sums up Chapter 4 recitation problems.